And basically, say suppose we have this kind of data points, and this is the simple toy example that I want to explain it here. And there are many ways that we can fit. Probably like easiest one is just like that. So it's a linear models. And but here, before we define the models, we make assumptions that this is linear models. There are several reasons that we can do. Maybe it's the data points the distribution is linear, but or this is the simplest way that we can think of. So we assume that it's a linear model first. So say we have in one-dimensional space, we have input and x and y is the output. So it will be here, it's going to be the inputs, it will be the outputs. And basically what I want to do is I want to find out the relations between the input and outputs based on the training data set. That's what I want to do. And I want to find out these, and it turns out this is, if this is linear models, and all we need to do is basically, or maybe you will say this, or I think I use theta not, probably, let's see. So now, only thing that we need is we need two parameters. So it's the problem is end up estimating two unknown parameters. So that's what the problem setting for the linear regressions. And let me see. And again, in many cases, we can start with any kind of functions as models, but in this case, so we're gonna assume that it's linear models to predict y, and we have input and outputs, and these two gonna be the parameters. And since say we have, suppose we have 100 data points, and I'm gonna make in the column vectors. That's something I believe that it make much easier. So this is the input, the column vectors, and this will be the output column vectors. Now, what I want to do, since we have many data points, I'm trying to form in the form of vectors, and we will do vector on or matrix calculations. That's what I want to do. And these the outputs, and this will be the, so this will be the linear models, and it will be, since I use this approximation because y is the actual values and y hat is the value that I'm trying to estimate or predict from the inputs. That's the notation that I have. So it will be y hat is going to be the predicted outputs, and these theta will be the unknown parameters. And as you can see in the titles, it's a linear regression as optimizations. Remember, in the first week, I spent some time trying to explain what the optimization is. That's the reason that I do. So here, what we can do is we start with the linear regression models, and now I'm trying to turn the linear regression problems into optimization problems. And how do you find these two unknown parameters? And you can think of these are the unknown parameters, or it will be decision variables in the context of optimization problems, if you guys remember it. So it will be the models that we have, and this is optimization problems. In that case, this is objective function, right? So I want to minimize, this is the actual output, the value, and this is the predicted value from the given input and the linear models. And there will be the distance or errors or discrepancy, and somehow I decide to make square of it somehow. So this related to square all two norms, things like that. And since we have m data points, I do summations for the entire data points. I want to minimize this discrepancy, square discrepancy, and I'm trying to minimize these values by having approximate or good number of the values of theta naught and theta 1. That's the optimization problems. So questions, what's the constraint in this case? What's subject to? So here is, in that case, because we can have any values of x, theta 1 and theta naught, right? So there's no constraint. So this is no constraint optimization problems. So we recasted it in the regression problems in least squared. And for let's this one is another tricky part. And we know that this is the linear models that we have. And I'm gonna have one here. Oh, before that, let me ask. This one says input and outputs, and this is affine transformations. This is not the linear transformation because we have the constant values here. So this is not the linear models, but this is affine transformations. And the tricky part is like here, say, I'm gonna make, if we do like that, we do that kind of matrix multiplication, right? So we get the same thing. And now this is, let me show you the, let me see. These, and if you have x of I as input, we can add 1. So we call it, this is feature factors or feature map. So we do mappings like that. And we know that we have x1 and x of n. We can do these kind of mappings. So I'm gonna call it, this is A, or this big, what is it, theta or phi matrix, I don't know what it is. And it turns out Y, these are the column vectors, including the entire outputs. We have these matrix multiplications. Now, let me see. This one is, we do optimization in element-wise. So we do summations. And here, what we can do, this one is the ith component of these vectors, right? And these, I want you to see the shape. And we have that kind of, and Y is, so that's the shape. So this will be another column vector. And we take 2 norm squared, right? That's the exactly same as the left hand side. What I did here is I I write it in a matrix form, It's much easier to understand. And we know that the solution is like that. There are many ways, several ways that we can derive these things. And here, the first way that we can do is we do, so let me see, this one is same as this. And we just do the matrix multiplications. And if that's the objective functions, we can take the derivative with respect to x. Because, so actually this is, yeah. And we'll get these as optimal solutions. So that's how we find the theta star. And using the least squares, and this is how we implement it in Python. And I mean, I suppose that you guys kind of familiar with this, and we have numpys and the matplotlibs to plot it, and we have np.arrays to define the data points, and you have reshapes to change to make sure that it's a column vectors, and these are how the way you're supposed to plot it, and that's how we plot it in the training data set that are given. And let me see. This is the solutions, right? A transpose A inverse A transpose Y, and this will be the zeta. And A is we know that A is that's how I define it. I use H stack. It stands for the horizontal stack. So here you use this kind of trick, or you can use the np.ones. Right? Actually, this I have to swap it. There's some typos, and this one looks weird, but it's a S matrix. So we change the type of A matrix so they can use this kind of notations to compute the transpose and the inverse of matrix things. And since we have thetas, we just plot it, and we can get this kind of things. Okay. So basically, in this semester, in these lectures, I mean, I will try to explain the theory first, and I'm going to show you how we are able to implement it especially in Python here. Later on for deep learnings, I'm going to use TensorFlow a lot. And this another advantage of using the Python is we have scikit-learn. The modules is already embedded in Python for the machine learnings, and you can find all the modules that you can use. So these are the big picture of, as you can see here, in classifications and the regressions and clusterings and dimension reductions, all the method that you guys can think of related to machine learnings. Probably you can think of this always exist. You just go and look for and just use them. For the regression models, and if we do linear regressions in sklearn or scikit-learn, and we have linear models, and you can import it here. And in the linear models, we have linear regressions, and I'm gonna define it here. And this is the command that you guys are supposed to remember it. It's a fit. You just put input and outputs. And basically that's what the linear regression is. That's the way they implement it in scikit-learn. And we define it by head. And these are the coefficient. And I mean, sorry. these are the coefficient and these are the intercept. So you can get the values later on. You can use these values to plot it. So you will end up getting the same plot. So what I did so far is I discussed what the concept of linear regressions, and probably actually you don't have to know how to compute. You can basically use a scikit-learn to implement it and to make use of them. So that's kind of the basic things that you're supposed to know for the machine learnings, and the classification is another topic. And there are many ways. Let me see. Actually, we have perceptron and SVM and logistic regressions. But here I decide to not to explain the SVMs because these two are eventually it will be related to neural net or deep learnings. But this one is kind of, so I decided to skip it. But if you guys, I think you guys already know the concept of Shuffle factor machines, but I'm gonna cover the only two method in belongs to classifications. The first one is perceptron. The second topic is gonna be the logistic regressions. Let's move on to the perceptron. I mean the concept of classification first. And let me see. There's the only difference. Let me show you regressions and classifications. Both of them are supervised learnings. That means for the training data set, it's supposed to we get the input and output, right? So since we know the inputs and the corresponding outputs or corresponding labels, we call them as this is a supervised learnings. We know so we're trying to find out the relationship between the input and outputs. But the only difference on the regression and the classification, if the y, if this is continuous values, it's a regression problems. If the y is discrete, it's a classification problem. That's the only difference. So when the labels or the output is discrete values, we call it as a classification problems. And we want to develop method to determine for new inputs which class should fall into or belong to. That's the entire purpose of the classification problems. We're gonna learn the perceptron and logistic regressions, although I strongly believe that SVM is one of the most effective way of classifying in machine learning, but I decided to not to cover it. All right, so let me see, suppose here, this is x of 1 and x of 2. What's the dimension of inputs? What's the dimension of input? Anybody? In these problems, in this. Suppose we have this kind of two groups, and everybody knows that. I mean, and in this case, in the regression problems, this one was the inputs and this one was the outputs, right? But in this case, the input is x of 1, x of 2, and the output is probably, I will say, is black and blue. So in these figures, the color represent discrete values as a labels, and we have two-dimensional inputs. Okay. And what I want to do, say we have these are the training data set, and somehow suppose we build classification models and trying to figure out what if we have this kind of new data points, whether the data point belongs to blue or black. That's the classification problems. I mean, this is, everybody knows that this probably belongs to blue. What I want to do here, I want to build models. In this case, it will be the classification boundaries. If these boundaries, if we set, I want to know whether this new data points is here, I mean, in this side, on the other side. That's the one way that we can build up the classification models. So here, if we have linear classification boundaries, we call it linear classification problems. Okay? So again, this is kind of this let me say, this will be the model for the linear classification boundaries. And I want to say, I want to know A and B. And another way that you can write it, that's kind of generalized line in two-dimensional space. So I want to figure out what the values of, if we are able to figure out these values of omega naught, omega 1, omega 2, that's the classification models that we can have. Once we have these lines and we know that any new data points, if this one is, we belong to the black, it belongs here, is if here it belongs to blue. That's the classification problems. And the first thing is perceptron. I think you already know this, and I'm not going to go in details, but what I want to do is these will be the feature of the inputs and define the weights. And this one is given, and these are the unknowns. And what I want to do, I will do linear combination of these. And I want to know whether this one is greater than or smaller than. These, the omegas are unknowns. And the physical meaning of this guy is for each features, x of I want to represent the importance of the features. And this one will be the threshold values, whether it's greater or smaller than, so we can make binary decisions. And that's how we check it. And this is the finalized one. Eventually, we do this kind of the calculations, and we put the sign functions, whether this is +1 or -1, whether this is on the positive or the negative values. Because we try to do here at this, the simplistic classification model is binary classification problems. So we'll do binary classification first. So that's we divide in this space. Okay. And again, there's another trick here. I'm gonna add 1. Then if we have introduced artificial coordinate like this, omega x of naught is equal to 1, I can simplify this like that. And remember, this one is starting from I is equal to 1, and this one is I is equal to 0. So again, in that case, what I can do, omega vector is x is, let me, maybe x naught, x1, xd. So it's another 2 column vector. And in the vector forms, these are, as you can see here, we just do multiplications for the element y's, and we do summations. It's the same as inner product. Same as inner product. So in inner product, let me see, the same as we do, if we put it, because we define it omega as a column vectors, we do transpose. So if we that way, so this one, the shape, sorry, the shape is like that. And here I transpose it. So we do that kind of matrix multiplication. So it's the same. And we can, this is also same. So that's the perceptrons. And we want to know these X is input and the, sorry, the Y is the output. And what I want to do is I want to know the proper values of omegas. So these here, I think I don't have to go in details because I already explained it in here. I want to know the distance from the line. So let me, these probably you have to take some time to understand. And let me see from, let me see that. Suppose we have G of X, omega transpose X, and I want to know what's the physical meaning of omega vectors. And it turns out that if we have two, say P and Q, two vectors on line of G of X is equal to zeros, and what we can do, omega transpose P equal to zeros, omega transpose Q equal to zeros, we subtract, right? And this means these is P and Q's any vectors on this line. And if we do inner product or transpose, if that's equal to zero, that means it's orthogonal, it's perpendicular. So the omegas, the geometrical or physical meaning of omega is it's normal to the line, right? It's orthogonal. So if we know the omegas, we know that omega value tells us direction of the line, but it's not like that in that way. Okay, that's the meaning of omegas. And let me show you here. If we have this, and here is the origins, and suppose we have omegas in that directions, and just remember at the end you will get this. That means this is the distance from the origin to the line, right? So that's the something that you are supposed to remember it. So this is the normal distance from the origin to the lines. And as you can see here, these are signed values. So we can get negative sign of distance as well. It really depends on the direction of omegas. Let me see. Now I want to know, say we have G of X equal to zeros and any or arbitrary values, the vector of X, and I want to know kind of this kind of distance. And I want to know the distance like that. And let me see, it turns out if you do some kind of math, this is something that you have to remember it. And H is here, this distance, or this distance is same as G of X and omegas. All right, so that's, I'm gonna use this one is when I explain the logistic regressions. That's why you need to understand this. And now let me see. For in that case, you have, suppose we have omega in that directions. We know that this will be the perpendiculars. And since we know the H is like that. And if we have X point here, and omega is in that directions, this one is positive. And here, if we have X, there will be the negative values. So let me show. So here, if we have, it will be this resume. And if we have, let me change the colors. G of X negative, it will be like that. And here is, this is linear boundaries to separate, to divide the 2D space into half and half. Yeah. So this will be the linear classifications boundary. Okay. That's why, and we know that G of X is omega transpose X. Good. That's why it's so important to find out what's the proper values of omega. And how do you find it? And let me see. Say we have this kind of example, we have blue and greens, and probably, as you can see, this one is the good candidate of decision boundaries. And say, suppose we have, I'm gonna show you say we have that kind of, then as you can see here, there's the misclassified data points. Right? So this is not good. Then what we can do, I can change the value of omegas, or I can update it until we find the omegas that is linearly separable. That's the idea of perceptron. So this here, we computed omega transpose X and to take the sign functions and pick if we do, this is H of X, and this one is the output, true labeled. If we have the good candidate of value of omega is probably these two values is gonna be matched. But if this is not a good values, probably we might have some misclassified data points. In that case, we have to update omegas. How? We follow this kind of rule. That's the perceptron rules. I think it'll be looks weird, but let me show you how to. So we have this one is we updated omegas. Let me show you in that case. Suppose the true values of y is +1. That means here it is omega transpose X or G of X is equal to 0, because we know that if that's the omegas, there will be the perpendicular. Right? But if that's misclassified, X, as you can see here, in X, this X is here. If that's X here, it will be the positive, but it's on the other side of omega, so it will be the negative. That's why it's misclassified. You guys get this point? So what I need to do, let me do, say this is what the perceptron tells us. So why don't we update omegas like that? And here we know that y is +1. So I'm gonna do plus 1 and x. That means there will be the x and the omegas. And let me see, I will do this kind of vector summations. There will be my new omegas. And since I updated omegas like that, this will be my new linear boundaries. And as you can see now, this is the omegas, and here is plus, and the other side is minus. And it turns out this value is plus 1. Right? So what I'm saying is that at least for the misclassified data points, if you follow this kind of rules, for that data points, it can guarantee that it's well classified. So, and another, if that is minus 1, you can do the similar patterns. So that's the perceptron. So the idea is that I want to update omegas whenever I see the misclassified data points. So I'm gonna repeat it for the entire training data set until there is no misclassified points. That's what the perceptron is all about. So again, I'm gonna randomly assign the omegas because we have to update it omega. So at the very first time we have to have some values for omegas, but we don't have. So I decide to randomly assign or initialize for the value of omegas. And sorry. So, and for misclassified points, I'm gonna update it. So I will iterate the process. So during the iteration process, let me see, suppose during some steps, this one was and as you can see, there is one misclassified points. And if we do this kind of update, this will be it will be move like that. So at the end, we satisfy all the all the training data points, and everybody will be happy. So that's the. So here is diagram for the perceptrons, and this one is probably, that's the only reason that I spent so much time to explain what the perceptron is, because here you have to visualize the perceptron like this, and these are the inputs, and this one is the actual output. For supervised learnings, input and outputs are given. Right? The unknown here is the omegas, the weight. So here at this, you will do linear combinations. And basically what omega transpose X or X transpose omegas. And you will get, plug into the sign functions, we'll get y of hat. This will be the predict values, and you guys can make comparison. And here probably is make comparison. And if the same, we don't do anything. If different, we'll do update, followed by this rule. So that's what the perceptron is, but more importantly, you have to look, these are the inputs and outputs. We'll do some kind of updates. That's what, and you're gonna see the perceptron a lot in neural net or deep learnings later on. So, because the perceptron will be the basic component or units. So, and how do you implement it? Probably you guys can, and I randomly generate data points like this, and we have binary classifications. One is red and the other one is blue. And for, let me here use H stack and V stack, and I use A matrix to get it, this the matrix. And here, that's how we implement it. And let me see, we have omegas like that. And we'll do iterations from, we'll check it. This one is X transpose omegas, and we'll check the sign. If the sign is same as Y, or if it's different, I will do update. That's how I implement in the Python. And probably you guys have to take a look at it at home to make sure you understand it. And if we implement it, and this is kind of, we visualize it in during the iteration process. And this one is, let me see, it's done. But as you can see, this is not a, I mean, this perceptron is give us one linear boundary that is able to divide or separate it, but probably this one is better, right? So there's the weak point on the perceptron. That's why I think in the next time I will try to explain what the logistic regression is. But another problem is, if, say, suppose we have some red points over here, and we cannot find the right solution for the perceptron because it's not linearly separable. Right? So that's the weak point for the perceptron. Let me see. And again, you don't have to write a programs from the scratch, and its perceptron is also embedded in the scikit-learn as well. Again, it's a linear models, and in the linear models we have perceptron, we have fit. We can use the predict values, the method to estimate it, to predict the labels. The question is whether this hyperplane is the separator is the best, and the perceptron finds one of the many possible ways the hyperplane separating the data if one exists, and of the many possible choice, the question that we have, which one is going to be the best, right? So it's related now is optimization problems. And here, this one is the motivations of logistic regressions. Let me see. This one is design functions in being used in perceptron. If you have data points here, it's +1. If that one is +1. It's divided by 2, but does not make use of any distance information at all. Because here we could do the same weight. So that's why, and now I want to utilize distance information from all the data samples. That's why I'm going to define it, and I'm going to discuss what the logistic regression is. Okay, so I'm done with the perceptron. I think you already know the major concept of that. And let me stop here. Let me see. You guys any questions so far? It's so weird that I'm keep talking and nobody's.
No, that's okay.
Okay, let me see. Let me finish up the logistic regression, so then I can probably Thursday I can talk about the TensorFlow things, because there are not many the materials for that. I think I can enough time to cover it. Let's continue on the logistic regressions. And again, it's for the perceptron, I only make use of sign of the data. And here, this is the big difference. And I want to see the distance as well. And the resistive regressions is not a regressions, it's a classifications. And don't be confused by name. And again, I want to find out linear classification boundaries like this, using the logistic regression in that case. And let me show you. Suppose we have only 2 data points like this, and this one is the square and this one is circles. And let me ask, which one's better as a linear classifier, you think? Number
First one.
Number 1 or number 2?
Number 1.
Why?
Yeah.
Why you think is number 1 is better?
Because there could be one really close to the border in number 2.
So let me
Because
go ahead.
it's about probability. It's another point. We have less chances that it gets in the other side.
Exactly. So because the Thomas series, we have less chance to get. So I'm gonna say probably this is more robust on some, right? So basically the simplest way we can say is I want to place the classification boundaries probably in the middle of or in the center of 2 clusters or 2 groups. In that way, if we have some uncertainties for each groups, probably this will be the less sensitive. So what I want to do, I want to do, so you all agree that number 1 is better. And let me compute this distance. Probably is different. And let's do, which one is bigger? Or the smaller or the same?
H1 and H2 is the same.
Same, right? So
yeah.
if you do summation of, 2 or all data point or distance from the line, we cannot tell, right? So because these are the same, right? So we cannot use the summations for the optimization problems. So the summation fails. And next thing is, let's say, I don't know, but do the multiplications. There's no reason, but I do multiplications. Which one's bigger in that case, in this case? Say we have like, if we do product, this one is 4 and this one is 3, right? So it will be like that. So even though we test only 2 data points, so this one is kind of give us the idea is that or suggestion or recommendation is we do distance multiplications and we pick the larger one or bigger one. Probably that will give us better classifiers than the other one. I mean, that's kind of the motivation that we can think of. And actually, you know that this, do you know this kind of inequality with the, or is that the arithmetic and, right? So, I mean, this is always true. And the summation is, it's a constant, right? These are the same. So it will be, this is constant values. And the product here is always smaller or less than or equal to. And we know that this equality here is when these two values are the same. So that means when we have maximized these values, we know that these two approximately is going to be the equal. That means the boundaries probably going to be located in the middle of it or in the center of, because these two values are pretty much the same. You got the ideas? So now what I want to do, I can compute any data points. I can compute it, the distance from I can compute the distance, which is d, and I will do product multiplication of entire data points. I want to do maximize it or find omega to maximize this, hoping that it will be give us the better classifications. That's the idea of logistic regression, right? So let me generalize it. So basic idea is to find the decision boundaries. Again, it's linear classifier problems to maximize these. So it's optimization problems. So since this is optimization problems, now I can tell that probably like A is better than B. So I can kind of get the best linear classifiers out of it. So again, I generalized it and increase the number of data points. And here use arithmetic and geometric means. Still this is true. And equalities when all the values are the same. I mean, this is not a, I mean, say like what if the number of data points are different, and but this one is kind of the thing that I'm trying to explain it to motivate the need of logistic regressions. So probably that's good enough. So locally speaking, this one is tends to positions the hyperplane in the middle of two class. And I said, remember this. And this one is omega transpose x, and it's kind of related to, is omega is here, so h is function of omegas. So what I'm trying to say is here, this is kind of we have x here is, so there will be the decision variables for omega transpose x. And next thing is we have to do something more. So for the distance or the omega transpose x, we can have values from negative infinity to positive, and we can get any value because it's a distance. But I'm gonna squeeze it, the distance from the 0 to 1 for several reasons. And I'm gonna use these sigmoid functions like that. So probably you guys, some of them are familiar or some of them haven't seen these kind of things, but this is the definition of the sigmoid functions, or we call it logistic functions. So this is sigmoid functions or logistic functions. That's why we call it logistic regressions. Okay. So we mapping it from these to the range from 0 to 1. So logistic functions like that. Let me write it. When z is, so this is will be gonna be the positive, and we have large values, so probably it will be zeros. And positive infinite will be almost zeros, so it will be 1. And when zero is, z is zeros, and probably this one is 1, so it will be half. So this will be the plot. So if these are the distance, the x, the met distance probably from, we'll get from 0 to 1. And at here we have half. Okay. And we know that z, probably, I'm gonna use this one, omega transpose x. So there will be the sigmoid functions that for that. So the benefit of mapping the via logistic functions, its a logistic function is monotonic. So for the, it will give us the same the optimization solutions because it's monotonic, and it's continuous. It's a differentiable, so it's good for the gradient descent method later on. And actually, this is the main reason that I'm using the sigmoid function, is because the value is always from 0 to 1. It's the positive. So we can think of as probabilities. We can think of as a probabilities. So this one is given the omegas and x, the x points, it's a conditional probability that x belongs to +1. Okay? So there will be the sigmoid functions, and the probability that label is +1 is this. And since this is binary classification problems and the same data points, and that value is the probability of being that label belongs to zeros is 1 minus. Okay. So again, by having the sigmoid function mappings, now we can think of that as probabilities. That's the reason. And here is, I mean, a lot of math and looks complicated, but I mean, I can, let me show you. Let me see. Okay, here, when x is given and this is the probability, and this is 1 minus, and this, and here. Let me show you. We know that y is either 0 or 1. So we can compactly write like that. Let me show you. If the y is equal to zeros, then here, this one is zeros. So this term is 1. And here it's going to be 1. So 1 minus h omega x. So this is same as in that case. And when y equal to 1, then this is 1 and these are zeros. So it will be h omega x, same as in that case. So that's how this. The reason that I can write it in this way is because it's a binary. The output is binary, and we have either 0 and 1. And since we have m training data points, we can write it this way, and we assume that all the data points are statistically independent, and we can write it. These are the joint distributions, and this is the marginal density probabilities, and we do multiplications. We assume that or independent. And this is the product. Yeah. But as you can see, these are the probabilities, right? So the value is from 0 to 1. And here, this one is from 0 to 1. And if we have, say, we have 100 data points, if we do multiplication of these values, the value is going to be extremely small. So it's for the computers, it's difficult to compute it because we have low resolutions. And in that case, we do the trick. We take the log on it. So we do these log likelihood, we do that. And again, this is monotonic function, so it's optimization problems, you're gonna get the same solutions, so it's okay. And good thing is now it's everything is instead of powers, it's multiplications and summations. So that's the log likelihood that I want to maximize, because that's the product of all the distance. You get the same physical meanings, but we do some we do the sigmoid functions mappings, and we take the log on it, and we do multiplications and we do take the log on it, and that's the objective functions. I want to maximize in this case, and if you find the solutions, there will be this will be my linear classifier boundaries that we found out of logistic regression, right? So again, this is optimization problems, and since this is so important or famous, or it's gonna be we're gonna use a lot. So there's a name. It's a cross entropy. We call it. So it's we name it as a cross entropy. So in neural net or machine learnings, for classifications, I'm gonna use a cross entropy for my objective function or loss functions. Now, then I don't have to go in details like that, but you have to assume that it's kind of logistic regressions things. Again, here to solve this kind of optimization problems, you can do gradient descent, or this is convex problem, so you can use the convex optimization method. But I'm not gonna do that here, but I'm gonna use scikit-learns to solve that problems. Let me show you here. Again, it's a linear models. We have logistic regressions, and there are solvers that you do, and you can fit it, so we can get all the coefficient, and that's how we plot it. So that's as you can see here, there's some the misclassified data points. It's okay because we try to optimize it. We can pick the best one. So even though this is, there's some misclassified data points, and you get the output of linear classifiers from the logistic regression. Up to what I did is we do logistic regression for binary classification problems. But if you extend it or make it more general problems, I think there are not many cases for the binary classification. We do multi-class classification problems. So for the multi-class classification problems, what we can do, we have two different methods that I want to explain it. The first one is, say, suppose we have three different groups, say C1 and C2 and C3. What we can think about, I'm not gonna just these two, it's binary classifications, right? So I will build up linear classifiers from either from perceptron or logistic regression, whatever. And I'm gonna take these only two classes into considerations to get another linear, and like that. That's how we do. Or another way that you can think of here, C1 and C2 and C3. I'm gonna think this one is one class, and these are the second class. So I can have this kind of boundaries. And let me use another colors. This one is the group, and these two are another group. I will do this kind of. So what I'm saying is that if we have multi-class classification problems, since we only know how to solve the binary classification, we can make use of binary classification outcomes to solve multi-class classification problems. That's how we do. And the second thing is, this is more important. The only thing that you have to remember is softmax. It's the same as logistic regressions, but you can think of it. We use logistic functions or signal functions. In that case, we're gonna so softmax is, you can think of, you can consider, or you can think of as logistic regress, the same version of logistic regression for multi-class classifications. That's, remember it in this one was the, and let me rewrite it. If we do multiply like that, right? If we have k class, now we have k omegas, the column vectors, and this is how we define it, softmax. And probably I'm not going to in details for the softmax, but I mean conceptually, the thing that you have to remember is conceptually the same as logistic regressions, but we're gonna use a lot for when you talk about the neural net or deep learnings for multi-class classification problems. That's the only thing that you're supposed to remember. For the summaries, this will be the last. Right, for the summaries, machine learnings, the major thing is regressions, we have classifications, and often we define it as looking at these two as optimization problems, and this will be the objective functions for the regressions, and these are the cross entropy or softmax will be the objective functions for the classification problems. How to solve this to find out the thetas or omegas, don't worry about it. We can use either Python or scikit-learn or TensorFlow, whatever. Okay,